All right. So yeah, today we're going to go over section, well, I'd say section 31, mod 3, but we're also going to kind of talk a little bit about the previous section, section 30. In the curriculum, you might have noticed it's kind of like section 31 in particular is much more of you like implementing how to do a logistic regression. So I kind of want to talk about a few things that maybe were not covered last time in, what's it called? In our section. So I did want to kind of bring this up. I'm going to pull up our old or our previous notebooks from last time. So let's see here. Green, I want to share. There it is. Okay, cool. I had to make it different from everything else because I have too many Jupyter notebooks and stuff open. So, and of course I lost you guys, but this is from last time. Last section, which I realized I never actually posted it to public, so I'll post that after this this session. But we talked about basically logistic regression and saying how it's essentially like moving from linear regression. I'm going to talk a little bit about like what that means exactly, or like what that similarity is, and so kind of it's a little bit different from the curriculum, but I think it's kind of an interesting way to think about it, and I think it's useful. But know that logistic regression is basically to do classification versus linear regression. We're basically, I mean, you could technically do some things, but the main thing with logistic regression is that we're using classification versus linear regression. We're looking for like an effect. So you can imagine like if we had something like weight versus, you know, blood cholesterol. So like let's say blood cholesterol is your y-axis and x-axis, this is only two-dimensional, is like your weight. Is that you might say, well, what's your blood cholesterol based on what your weight is? Well, the linear regression, as you increase, I guess I'll go ahead and draw this out. So if I go ahead and draw this out, if I had like a linear regression here, I don't know why it defaults to this ugly looking green, but if I have my y-axis here, which is like blood cholesterol, my x-axis is one of my features. In this case, I'm only using one feature, simple linear regression. And this is like my weight. So the weight of a person. And then y is some, I don't know. I don't even know how blood cholesterol is measured. But let's say there's some number that's associated with blood cholesterol that increases over as you have bad cholesterol. I'm not a doctor, I don't know. But I'm just blood clots, right? So as you might have some data points like this. You know, maybe you have some outliers where someone is like, you know, very, very skinny, but they have, you know, very high blood cholesterol. You might have someone who's actually very much heavier, but they have low blood cholesterol. You know, you might have some outliers like that. You then draw your line of best fit. I know those dots aren't great, but at least they're better than nothing. And I draw my line of best fit. And then we say, okay, using this line now, we can figure out, well, if I have this weight, I predict that I will have blood cholesterol of this much, right? Linear regression has this continuous line. Logistic regression works a little differently, where instead of, and I'll just draw a little bit below here, logistic regression, oops, oh, we'll make this work. I didn't mean to make a line, there we go. So logistic regression basically says the y-axis essentially is a binary operation, says, and I'll put it a little bit above 0 just so you can read it, but just know it's usually at 0. It's like, okay, like you, let's say heart disease. So you either have heart disease or you don't have heart disease by some measure, okay? So say, you know, you have no heart disease, which is good, and then you have heart disease, which I guess is bad, okay? And so you're classified basically, if I have these different points, you're either classified here or here, right? And this right here, we'll keep it as weight. So this is our feature still. So depending on your weight, you might have heart disease or not. So maybe most people who are lower weight, you know, I don't know if this is necessarily true for this pattern, but I'm just gonna make it up, is that maybe if you're lower weight, you are less likely to have heart disease, okay? Maybe some people who are like low weight, they still do have heart disease. So for example, this person's like, let's say 120 pounds and they still have heart disease. And then as you get higher in weight, maybe you're much more likely to have heart disease. So you can see if you're a certain threshold right here. And the way we fit this has been classically, or at least we just learned last section, is logistic regression. And basically it creates this logistic curve, which looks like this little S-shaped curve right here. And this basically, this continuum allows us to think of it as a probability. Basically 0 probability that you have heart disease, and then a 1 probability that you do have heart disease. But of course, if you're like right here in the middle, so for example, if I had some point that was like about right here, where you're like, well, this weight's not super high, but it's also not super low. And so you might have a probability that's like right here, okay? This basically is saying, okay, that means this person at this weight, based on our logistic curve, is the probability of, let's say, like 0.7, okay? And so essentially this allows us to say, okay, what's the chances of you having heart disease? And this is why logistic regression is usually best used with binary class. So like you're saying, you're either this or that. You can do logistic regression like I showed, I think, last time. You can do logistic regression with multiple classes. So let's say there's like heart disease, no heart disease, and let's say there's another third one called like at risk or something like that, or some other like third. That's probably not the best one because that's more of a continuum. But if you imagine there's basically, I think there's the example I gave last time was with the iris data, which is basically about flowers. And so you might say it's like, oh, are you, I'm just gonna make something up. It's like, are you a red flower, a blue flower, or a yellow flower based on your features? And those are 3 different classifications. You can do logistic regression. You just have to add a little extra to it. Basically, it's a 1 versus all. So you're either a red flower or not a red flower, which would be the other 2. And then you would say, oh, I'm a yellow flower, or I'm not a red yellow flower, which would be the other 2 again. So that's kind of like how you could do logistic regression for multiple classes. But that's not something, usually we just talk about just 2 because it's simple that way, right? So again, that's the basis of what we're doing with linear regression. So I just wanted to review that before we get into it. And I think last time I had an example, I had an example of implementing logistic regression. So in this case, I actually used sklearn. In the curriculum, we actually have you do actual logistic regression and figuring out the thing. In reality, you probably will use this much more often because it's optimized. Basically, it's built on top of NumPy and other, features within Python itself that allow you to basically be like vectorization, and there's all these amazing things. So basically, I say it's like a bunch of smart people who are definitely smarter than me, who had a lot of time, who've worked together over a few years, have made this. So I probably will use this over than actually making my own. But just know that this is probably how we use it. But I had my logistic regression here. I got the data. This is the data, iris data. In this case, I used 3 different classes. Is that right? Yeah. Okay, and I just did all the classes here, and I did a logistic regression, and basically could predict, as I ran this through, see how well it predicts it, and you saw it. It's like, oh, okay, did pretty well, about 97% on the training, and then I think it ended up being 93%. Yeah, 93% on the testing. So that's how you would implement it, right, in code. But we're gonna talk about like how it works, so you understand, like, well, what's going on when I do this, right? So I want to pull this up, and of course I can't see my own stuff now. So, all right. So the first thing I kind of want to talk about, since this is what starts talking about the curriculum, basically the curriculum goes through 3 steps. It says, all right, remember MLE, maximum likelihood estimation, and then it goes, remember gradient descent. It's like, all right, now we're going to use MLE in gradient descent to figure out how to not optimize, but figure out the logistic curve, okay? And so we're going to kind of walk this through. So I'm going to do similar steps, but I'm going to talk about it differently than the curriculum. So just know that the stuff I'm talking about isn't necessarily the same way the curriculum presents it, but it's the same concept, and that's what I want to go through. So MLE is the classic one that, oops, sorry, I want to make sure you do that, okay. MLE is the classic one that everyone says in, like, I don't understand, what are we doing with MLE? Like, we can write down the equation, I know they're supposed to estimate it, like, but what is MLE? And the curriculum wrote in words, which is actually a really good example, but I think it helps visually. It says if you had a coin and you flip the coin and you want to figure out, is it heads or like, is it a fair coin? Is it 50-50 for heads and tails? You would use basically, MLE basically says, all right, let's see what our data actually says and use that estimation. So what this really means, and I'm going to use a histogram example for this. So imagine you have this line of data. So this is just like X, like let's say the weight, okay? And I just have a bunch of data points. All right, I have one data point here. I have, like, this is like weight. Oh, okay. So we'll use the same thing as we did like with heart disease. So this is our weight. And now what we can say is like, okay, we have a point right there. We have a point right here. We have a point right here. We have a bunch of points right here. And then maybe we have like maybe one right here, one right here, one right here. So if you look at this carefully, like along that x-axis, right, is that it looks kind of normal. Okay, and this is kind of like what MLE is. It's like, well, imagine it is a normal curve. Say, well, what's the normal curve supposed to look like? So what we do is like, well, let's figure out what the mean is. And so we essentially say, all right, let's go ahead and start drawing a bunch of normal curves centered at each point. Okay, so if we say like, okay, like at this point right here, a normal curve like this, and you figure out what is the probability that each one of these would be on here. So you can see the probability is very, very low. And then we draw another curve here that's centered at that point. It should be the same size, but I'm bad at drawing. But same size right here, and you say, okay, what's the probability that these points would be part of this curve? And essentially what you do, you have that probability, and this value is going to be some number here, and you multiply essentially each of these probabilities. Say, okay, the probability of this being here, okay, there's a certain probability based on the normal curve, certain probability based on this normal curve, and you multiply all this together to get one number. And then you have another number here based on this curve. And so essentially what you do then is, I'm going to draw it right below here, is when we're talking about the probability, we say like the probability of this being here, I'm just going to make up some numbers, so it's like 0.5 or something like that, right? There's a 50% chance that it's at this exact center. And then there's like, oh, there's only like a 0.1% chance. And there's a 0.0001% chance, and it gets very, very small. And you multiply all those together. This is called the likelihood. So this number is going to represent something called the likelihood in statistics. And I'm going to spell it right. Okay. So that's the likelihood that this normal curve represents this data. So you can already see it's like if we have very, very small probabilities, this number is going to be really small compared to other numbers. For example, if I drew another normal curve that's centered around this data point, okay, you're going to see like, well, it's still going to have some small probabilities, but most of them are not going to be very small. So we're going to see that this likelihood is going to be very small versus this likelihood of this histogram explaining the data is much bigger. So what we'll see if I kind of drew this out, if you imagine like, okay, those are my different data points right here, where basically where my mean is centered at. I say, okay, well, it's a very small likelihood that this histogram's mean is centered right here. And then as we move further, it's like, well, it's a little bit better over here on this part right here that this histogram is like more likely. So you can imagine this y-axis here is my likelihood. I want to spell like. Okay. That's my likelihood. And so you see, as we get kind of closer right here, you can see this is probably like the optimal right here, right at this point. This is the highest likelihood. And then as we move a little bit further again with this histogram, it's like, oh, we have the same problem. This histogram is not very likely to be over here. So you would basically say, okay, here's my likelihood, and basically say, oh, this right here is the maximum likelihood for the mean to be here. So essentially, oh, that means this point right here is the most likely, and we can see that position. And so that means that position right here, if I drew straight lines, but basically said that position right here is the maximum likelihood. And this is all based on the estimation of our actual data. This might not actually be true. Maybe we're like, maybe this is this point right here. Maybe this is super, like this is the actual truth. That's what it should be. We just got very, very unlucky. And we got like, imagine if you flip like 50 tails in a row versus one heads. You know, you might think, oh, that coin is unfair, but maybe it's just by pure chance, right? That's kind of what we're doing. It's like, well, this is very unlikely. So we're looking at the thing that is the most likely that's happening here. And that won't necessarily be the truth, but it's at least based on our data, our best guess. And as you increase more points, hopefully by the law of statistics, or probability, I should say, basically as we increase the value of the number of points that we do, like basically the more coin flips you do, the less likely, or like you're basically more likely to actually get the full truth of like what that coin represents or whatever you're measuring. Okay, so that's the idea of MLE here. Basically, it comes down, you take each data point and you say, all right, based on the distribution or whatever I'm looking at, let's calculate the likelihood, which is essentially just all the probabilities of my data points. The probability of this data point happening with this distribution, this data point happening with this distribution, basically multiplying all this together, that will give us the likelihood. And then we say, all right, let's move our distribution, and we could do this continuously too. We could have done like the likelihood, something like this. We move that distribution across and say, all right, what if it looks like this? What if it looked like this? What if it looked like this? And you do that and you basically calculate the likelihood of each point, or sorry, the likelihood for each distribution based on the points. And then you say, all right, this is my total likelihood curve. and you say, all right, what's the maximum of this? Okay, and that's basically what we're doing with MLE. Okay, now the way you actually calculate this turns out to be, you'll remember if you think of this very like, if you think back like when we did this, I can't remember when we talked about MLE, I think it's like back in mod 2. But if you remember, we actually did the log of the likelihood. And the reason why is because we do the log of likelihood, it's easier to calculate the derivative. That's pretty much the only reason why we do the log, and it gives us the same position. It might make this log likelihood, like if I took the log likelihood, it might look something like instead of something like this, it might look something more like this thing. But the point is that the maximum, that maximum point will still be at that same x point right here. And that's why we actually take the log right here. And it just makes it easier for us to do a derivative. Okay. So any questions about what I kind of explained? Hopefully that kind of gives you a firmer idea of what we're trying to do with MLE when we say maximum likelihood. We're basically saying, what is the best phrasing? Sorry, so my question?
I have a question. So I have a question about what is being estimated. The maximum likelihood is not really being estimated, it's being calculated with some confidence, right? And it's and that's being used to estimate something else. So
it's kind of weird is that the MLE, the E part, the estimation, comes from the fact that we don't know if this data actually is, quote unquote, the true description of the real world. We only are estimating it based on the fact that we have these many points, if that makes sense. So like, for example, I can only estimate if a coin is fair, you know, by flipping the coin. If I happen to flip 10 times and I get 7 heads and 3 tails, I'm basically estimating off of that coin flip. So I'm trying to figure out, it's like, okay, like based on my data, what is it most likely? It's most likely essentially that my coin is not fair and has a different distribution than a nice 50-50 flip. So that's kind of what that estimation part is from, if that makes sense.
I see. Because it depends on what you have to work with.
Exactly.
Okay.
And that's why, like, I think in the curriculum, like on the section 31, it talks about having a coin and you're flipping it and you find out that it gets heads 0.55% of the time. That's all, like, you can't, there's no mathematical way to say, well, it really should be, you know, 0.5. Basically your data, our data, like you can't kind of change that. And that's what the estimation comes in. This estimation really comes from the fact that probability is based on estimation. Is that?
Okay.
Yeah. So, and this estimation obviously gets better as we increase the number of data points. So the more data points we have, the more confident our estimation is closer to, quote unquote, the truth, which is already debatable, like what is truth? But anyway, that's what that estimation part is. So that's the idea of maximum likelihood. And so one thing to kind of note about this for maximum likelihood, it doesn't have to be this normal distribution. It can be whatever distribution you want, which includes the binomial distribution, which is what's going to happen when we do logistic regression. Basically, we do the maximum likelihood on a binomial distribution, but the same concept happens. In fact, we could do the same thing. This is actually finding the MLE maximum likelihood of the mean of a normal distribution. We could also do this on a, what's it called? Like on the standard deviation. So kind of quickly, I want to show you guys a few examples since this will come up, you know, different, like MLEs used for different things, but especially logistic regression. Okay. So we have like our data points here, and I'll just quickly draw out some fake data points again. Okay, so we have all our data points here on this different x-axis. This could be like weight, for example. And then it's like, well, we don't want to estimate the mean anymore. Let's say we want to estimate instead the standard deviation. So I'll just put sigma. Okay. So what we would do here, we basically would draw, let's say we figured out, it's like, oh, the mean should be here. Okay. So I draw my first histogram, or not histogram, sorry, normal curve. And then I would say, okay, let me change the standard deviation. Well, the standard deviation makes it look more like fat, like this, like more squashed. Okay. And it's like, oh, well, let me have a smaller standard deviation. So I'd have something like this. And basically I would have for each one of these histograms, what's the likelihood of basically of these points. So this one, for example, might have a likelihood, I'm just gonna make up a number of like, I don't know, like 0.3. And this one has a likelihood of something like 0.7. And this one right here has a likelihood of like 0.5. 2. Okay, and so basically you would draw all these different histograms changing the standard deviation. Basically, you could have like a continuum. You could continuously change that standard deviation of the histogram and say, what's the likelihood of this one? What's the likelihood of this one, this one, this one, this one? And you would basically have a graph of your likelihood. And it would be something like this. Okay, and basically you'd figure out, okay, what's the maximum there? And then you do the same thing. So just know you can do it with whatever kind of distribution, whatever you're kind of looking for. So just wanted to show you guys what that looked like. Okay, so now, important part, let me just save this one. I don't know if I can do a new one. Can I do a new one? What's this do? No. Create new board. Why not? Okay, so now I want to kind of extend this now for logistic regression. So for logistic regression, remember the likelihood. And in this case, it's a binomial. Now note that technically you don't have to have a binomial distribution to figure out the likelihood, but it's usually what we tend to stay with. Basically, do you have heart disease? Do you not have heart disease? You know, yes or no, essentially. So usually we'll have it as basically the likelihood is just for each point, the probability for each point. I'll call it P, you know, the first point times the second point probability, the third point probability, okay, and so on. And then I feel like I should show you guys this. Okay, I'm gonna pause this for a second. So imagine I have a our graph that we would do our logistic regression on, and I have my points. For example, this is like no heart disease, okay, and this is my weight down here. So we have our point here, our point here, our point here, our point here. Those all have no heart disease, and I'll put one random one right here. And then maybe someone who's really skinny still has heart disease, right? But as you get into higher weights, they're much more likely to have heart disease, right? So we have my little symbols before. Has heart disease, bad heart, good heart, okay? So this right here, basically, okay, this right here is saying like, okay, these are all classified as heart disease. And I guess if I was consistent, I could have done this. I'm trying to make these points so it's easier to see when we draw the likelihood. Okay, and so what we showed before, we kind of didn't say anything like well, how this happens, but we're just going to draw a logistic curve. So we're going to draw a logistic curve that looks like, I'm making it really extreme just to make it kind of hone in the point. And so this logistic curve right here basically is saying the probability, and we're going to map down each of these points to here, which will tell us on the y-axis the probability. So you can see here, this one. So it's not already 100%. And you can see from here, if I map this down, we get to this point. Okay. So you can see here basically it's like, oh, this probability is like 0.99, right? And maybe this probability right here is like closer to like 0.5. Okay. So when we do the likelihood, what this will look like is like, all right, we first take in, I'm going to go ahead and erase these guys since this was not going to be good. Is if we take the likelihood is just essentially, all right, the probability of this first guy. So I'll just call it, I'll call it P0, okay? P0 times P1, which is this one, which is, and then times P2, and then going so on all the way to, we'll just call this, what's this, 1, 2, 3, 4, 5, 6, so P5. Okay, so basically all these probabilities multiply together, and then we have to calculate the probabilities that these were correctly put in together. And so this is the probability. Okay, now I'm gonna put in not P versus just regular P. So remember, P represents the probability of actually having heart disease. So the probability of having heart disease. And this right here, we want to say, well, what's the probability of these having heart disease? In this case, it's very close to 1. So I'm going to put in 1 minus P. So 1 minus P of this guy right here, and this will call like P6, times 1 minus P7. And so this would be a relatively low probability to be like having heart disease, or not, sorry, having heart disease. So 1 minus P would be having the likelihood or the probability of having heart or not having heart disease. Oh man, okay, if that makes sense. So that's why I'm multiplying here, basically like what's the probability of this being correct, essentially, right? And so I do that based on the logistic curve, all the way through all the different p's. So that's my likelihood. And I get this number and I get some value, okay? And this is where we can actually say, well, okay, we can do this part and then we can figure out those numbers. But an easier way to do this is that we kind of showed this, I think back in mod 2, is that we can say, well, if we take the log likelihood, it makes it really easy for binomial distributions. So the log likelihood, if we take the log of this thing, well, this essentially just ends up, well, I'm going to go one step further. All of these p's, okay, we can essentially say, what's the probability of this happening? Well, we can just essentially say p to the power of n number. And we'll call this one 1 minus p is the probability of m, the number of times this happens. So if you take the log of this likelihood, we end up actually getting n times the log of p, oops, plus, well, we'll see in a second, plus m times the probability, I'm sorry, times log of 1 minus p, okay? So this ends up getting like this nice value right here because we got rid of this thing. And when we take the derivative of this guy, okay, we actually end up getting this nice, checking my notes to make sure I got that right. Yeah. When we take this probability right here, or the derivative to find this maximum likelihood, right? Because in the end, we just want to find the maximum, which is why we're taking the derivative, okay? But if we do this, it's like we simply just get basically, it's like, okay, well, that's n. In this case, there we go. We'll have n times log of p, okay, minus, and it'd be like, or say plus 1 minus p times m times the log of 1 minus p. Okay, and that basically allows us then to say, okay, like, well, we have this part right here, we can get that negative part, and I feel like I wrote something wrong down for my guy. So I want to double check that I have this right. But basically, when you take this derivative, you will get an easier form of writing our maximum, to find our maximum likelihood. Oh, I think I misspoke. I should say this is 30, not 31. My fault, guys. Okay, so anyway, put this on pause right now, but you can simplify this further, essentially. And when we get that more simplified version, we can actually do some quick calculation on it. Where are you? I wrote my stuff down wrong, guys. I'm sorry.
That's okay.
Thank you. But anyway, I'll put this on pause until I pull that up again. But just know that we can take the derivative, and derivative is a lot easier to calculate. And I definitely didn't write this part exactly right. But once we essentially have a way to figure out, like we have an equation essentially to figure out, I'll just call this L. We'll call it lowercase l. Okay. Once we figure out this equation that's L, we say, all right, cool. We just need to maximize this part. And once we figure out, hey, we have this, we can use gradient descent to say, all right, let's find the maximum value. Okay. And of course, when the maximum, we can basically, when we're doing the gradient, we can also find like the minimum, right? So we can flip that over and find like that value. But once we figure out like what the equation is supposed to look like, we can actually use gradient descent to proceed further. Does that make sense?
So are you using the gradient or using the gradient descent?
We'll use gradient descent, which, I mean, gradient descent uses the gradient, but the point is that we needed some formula, basically. So if you remember back when I showed the example of like MLE in general, is that we had some kind of like, if this was the likelihood, and we had some value like, you know, this, so I had to do those different points. So, okay, that's the likelihood, and there's some maximum value right here. This is likelihood. Is that if I want to find the maximum here, I would have to take the derivative, second derivative, find the maximum, stuff like that. And I could technically do that, but gradient descent allows us to essentially find that maximum or minimum, depending on what you're looking at, right? basically allows you to find that min or max by just basically skipping around versus me analytically figuring out the derivative. So you remember before, the steps to find the maximum would be like, all right, we have this function, let's call it likelihood. I'll call it L, capital L. So our capital L, we have to take the derivative, right? I'll call it just f(x) of L, set that equal to 0. And then we figure out whatever the value of x that gave this, right? So this is the x part right here. We figure out what x is, and then we have to feed that in and say, all right, what's the second derivative of that equation, L? But then plugging in, we'll call this, we'll just call this xc. So whatever that value of xc, which is this guy right here, we figure out what this xc is, and then we say, okay, is xc, is that greater than or less than 0? And that will tell us if it's a maximum or minimum. So this is the steps that we normally would have to do. The problem is that this equation right here might not be easy to solve like with the derivative itself. And finding what that xt is right here is actually kind of difficult for computers to do. So we can do gradient descent to say, well, okay, let's just kind of skip around until we figure out what's the right kind of value. So what I was going to show you guys next was how we would apply gradient descent to figure this. But the point is that once you have the equation that you want to maximize or minimize, we can use gradient descent to figure that out. But in order to do gradient descent, we have to know what the first derivative of the first equation is. So if I have my first equation like this, which is the log likelihood, so I have the log likelihood, I take the derivative of the log likelihood. Once I take the derivative of the log likelihood and I can write that down, I can now do gradient descent really easily.
I think what I'm asking about is that I think of gradient descent as finding the lowest point. So if you're trying to find the highest point, I would think that it's
yeah.